Consider a wire. This wire is going to, in a basic sense, look like a rectangle. This wire is going to be placed into a magnetic field. So I'm just going to draw two magnets. I'm just going to label this one on the north side and this one on the south side of the magnet. What we will then have is a magnetic field going across this way from north to south, and we're going to have a coil in between. Now let's say the current on the coil, current I, will go up, through, around, back down, and out through the other side. This coil of wire, I'm going to say that it's going to have A, B, C, D. So that means that our side length here is AB, our side here is BC, CD, and DA respectively. What can we say about these different lengths of wire? Well, our length here, BC, is going to be parallel to the magnetic field. Actually, the same can be said regarding AD. Now, we should remember that when dealing with the right-hand rule, if the components are parallel, like BC and AD, to our magnetic field, no force is applied to them. This means that the only force is applied to by the lengths AB and CD. Now let's have a look at the magnetic field as it passes on. So I'm going to take a snapshot at the front version, and I'm going to see how those wires interact. So I'm just going to draw it at its initial starting position. So I've got two wires here. Now if we look at this, the current is going in at A, so it's going to have a cross, and it's coming out at D, so it's going to have a dot. Now these two are going to be connected, and they're going to be freely able to move around a center point. Looking at our diagram, we have a magnetic field that comes across. So what does this do regarding our force? Well, using our right-hand rule, we have a current that's going in, our field is going to the right. That means our force is going to be pushing it down. And on the other side, our force is going to be pushing it up. So as it's fixed around a center point, our coil of wire is actually going to start rotating. As that force applies to it, it's going to rotate around, and we're going to end up at a new position. However, the force here is pushing and pulling in the same directions, as our magnetic field is still running in the same direction. So again, the coil is going to rotate. Now, it's going to be vertical at this point here. Our magnetic field is still traveling in the same direction, except now our force is actually pulling it up and down. So it can't move in any direction from that point. In fact, if we were to draw the next one, as it continues to rotate around, it's still actually going to be pulling it up and down as the magnetic field goes across. That means that this point here would be at a point of equilibrium, and our motor would stop spinning. We would end up not moving our wire anymore, and we would just end up with our wire actually setting in a vertical component looking like this. And what use is a motor that doesn't actually spin? It's just going to sit there and do nothing. So what actually happens at this point here is we end up with two brushes. These brushes sit to the side of two coils of those lengths of wire. These are my brushes, and we end up with two slipping rings. So these rings can spin freely, and these lines back here, this bit here and this bit here, are the coils that go up here. That gives us a set of rings that attaches here. They don't complete a complete circle, they're two half rings. This means that when our wires come into contact with those brushes, it'll actually be able to spin beyond this point here. Because when it gets to this point here, the current is actually going to flip. The current here is now, due to the brushes, traveling in the opposite direction. And we're ending up with the wires traveling in the same direction as normal. This is very useful because if it didn't do this, again, we would end up with that equilibrium point. At that equilibrium point where it's completely vertical, in a sense, we have no current traveling through, because that's where our brushes are not in contact. So it is its own momentum that actually keeps it traveling in the same direction. Because we have a force pulling it upwards all the way to that point, the force is still being applied until it reaches the vertical. then it's just continuing its spin. It then changes onto the other brush and it's able to continue being pulled down by the forces involved. That's how a DC motor works, very simply. Now we're going to derive the equation telling us how much force is going to be able to be achieved out of a DC motor. What I'm going to do now is just bring in our diagram of a DC motor, and I've just labeled this whole side here A and this whole side here B for simplicity. Now, what we need to think about is what torque is. Torque is a moment of force about an axis. So torque is equal to RF. R being distance from center, F being our force applied at that distance away from the center, and our tau here is just our torque. So if we look at this, we also know that our force, due to our right-hand rules and our knowledge of electromagnetism, is going to be the perpendicular component of it. So that's going to be equal to RF sine theta. So as our wire rotates up, we're going to get a perpendicular component of our magnetic field. So that part there is going to give us a theta component. So it's not 100% in the magnetic field, so we only get a component of it. When we're talking about the torque inside of a DC motor, we know that that is going to be dependent on the current. We also know that we have two wires here and here that are perpendicular to the magnetic field. Our force that we're going to be able to get from this is going to be 2I, the current flowing through, B, the magnetic field that goes past, A, because that is the length of our wire, and we have two of them, and sine theta. Because sine theta is telling us at what angle that coil is sitting at is depending on how much force we're getting. So let's look at the maximum force. Well, that's going to be when sine theta is equal to 1. That just gives us our force when it is perpendicular is going to be 2I B A. Our torque is going to be equal to the radius force perpendicular. Well, our radius, if we look at our diagram, we will have a single line that goes through the center, and that's where our axle is going. So that means that our radius is actually B on 2, which gives us, once we substitute our force into it, that 2IBA times by B on 2, simplifying all that out, gives us IBAB. Now, we have a coil or a rectangle worth of wire that's sitting inside of it. So if we say that IAB, where A is the area, so that's just going to be equal to A times B. I is our current, and B is our magnetic field. However, we never make a DC motor with a single coil. The amount of torque that we're actually able to get out of it is going to be very, very minimal. So the amount of torque that we can actually get out of a motor will have an N number of coils. And I've re-added in sine theta because we can figure out at what angle from horizontal the amount of force that we're going to be getting.